is Carlos Arellano, and today I'm going to talk about convolution to the kernel and convolutional neural network. So let's take a look at this assignment. On the first part, we are going to use image convolution. Here we are importing necessary packages and libraries. Here is the link for the images we are retrieving from. This is we are displaying the images, and as we can see, it's a car. And here we are going to print the array. It's 140, 359, and the color channels are not the same. Now here we are changing the color channel. We are going to visualize the values inside of the resulting array, and here we have the convolution with 2D kernels. And let's get started by it here. So we are creating our padded array with 2 columns and 2 rows. We are comparing the array. Here we are applying the kernel to the array values. Now we can see the image. It's more white right now. First of all, if you remember, it was a red card, then we changed it, the channel. Now we have a new plot. We are using a grade, and now here we are going to squash out the values between 0 and 255 range. Here we have the function for our convolutional 2D kernel. Now we are applying line detection right here, as you can see, and let's get started with this part. So now, as you can see in this section, we are detecting lines for this car. It's specifically here only horizontal lines. As you can see here, it's highlighting these horizontal lines. So notice we only see these lines right here. We can see much more, and then we are going to apply a 45 degrees to detect 45 degrees lines. So let's take a look at this. So first of all, I named the array we are creating as first degree kernel. This is the kernel we are going to be creating to detect 45 degree lines. This is the array that we are going to implement. Then we are going to apply the kernel to the image. Here, as you can see, we are using the convolutional 2D kernel. Here we are passing our input image array. The kernel, we are passing this kernel that we created right here, and here we are plotting our image. Now we are going to do exactly the same, but this time instead of 45 degrees lines, we are going to detect 135 degree lines, and we can use this. We are creating here this kernel with this array, and we are going through the same process as we did before. Now we have the edge of detection to kernel to image and plot the output. Let me show you more information. Here we are doing exactly the same. Here the first time we are displaying the edges, as you can see here. Now let's notice the difference in this second images. We can notice the lines right here, and with the shape, and here in the last one, now we can see the car with more color, or well, actually not more color, but it's highlighting the lines in the kernel, the edges. So let me show you something, and we are applying this Lapsian operator right here. This is the Lapsian operator. Let me go through it. It's right here. So it's applied for edges. Then we also are using these at detection right here. In this example, we have a house, as you can see, it's -1, and here we have 8 in the middle. It's exactly the same as what we are doing right here. We are highlighting all the edges. As you can see here, it's the same as in this example. So now let's move on. Here we have also more exercise as we did before. For instance, 135 degrees lines, 45-degree lines, and this is a good resource that we can find more examples of what we are doing right here. So now we have understand what a 2D kernel, convolutional 2D kernel works. So it's time to create our convolutional neural network or our model. So here we are importing all the necessary packages and libraries. We're preparing the data set. Now this is the part where we're building our convolutional neural network. We are saying the model is going to be sequential, and here as you can see we're saying convolutional 2D, and here we have 32 nodes, and we are using three rows, 3 columns matrix. The padding here is going to be same, but let me go through this image to explain this concept. Okay, so what we are doing right here, we are passing our data. In this exercise, we are using the information from this link. This is the data set C410. So we have here the information. This is our input layer, or in convolutional neural network we call them input channel, and the last one, this yellow here, it's gonna be the output channel. Right in the middle we're gonna have the convolutional layer or nodes right here, and what we're doing is we're passing this information through these nodes, and here we're adding a matrix of 3 times 3 randomly assigned with these numbers, and the process that is going to go from this node to the second one on the next layer, it's going to be the operational convolutional. So what we are doing here, it's the same as here. Here we have 32 nodes, and we are filtering this data because we want to know through some information, as we did before right here, that we wanted to know the edges, or that we wanted to know the lines of this structure. Here also passing our parameters in right here in our matrix, and here the padding, it's equal to the same. Let me explain it a little bit. So I found here we have this demo, but now I'm using the fashion M&S exercise just to go explain the concept of convolutional neural network. So the first part that we have is our data, or our input data. Let me go with this small exercise, and then we're going to jump to the demo. So here we have, let's say, the input of 4 times 4, and we are saying the same here, but here we have 32. In this example I'm just using the 4, and here as you can see the matrix of the 3 columns and 3 rows, these are going to be the filters we are applying to our model right here. And since the model, the filter, sorry, it's 3 and 3, the model, it's going to do this. It's going to go to this first analysis, then it's going to jump to the second one, then it's going to go 1 level down, and then we are going to move 1 level right, because this is the size of the model. So we are applying this filter 3, and the output is 2 and 2, because as I mentioned before, here we are going to be displaying this one information one level, then we are going to have this one level more, and here we're going to have another, oops, right here, and lastly we are going to have this one right here. When we talk about padding or not padding, it means that the output, when it's the padding equals same, the output is the same size as the input. So we are going to actually do padding right here in our model. So we are going to have the same size as the input and output right here. Just one more time. So we are going to keep the filter 3 times 3, but this time, as you can see here, we're going to have 1, 2, and 3. This is all 1, then we're going to have 2, then we are going to have 3, then we are going to have 4, and so on. So in this example, the output is going to look like, when we are padding, sorry, the output will look different. Oh, sorry about that. Oops, my bad. There we go. Okay. So when we add padding, now the output, it's gonna be the same size. Here is going to be just one more. There we go. So now the output, instead of being 2 times 2, it's gonna be 4 times 4, since we are adding padding right here. So this is what we are doing in our model right here. When we say I want to pass 32, I want the filter to be 3 and 3 for 3 columns and 3 rows. Then I'm saying the padding, yeah, I'm going to add padding. I want the output to be the same size as the input. Here we are using the activation function for our ReLU, which is going to bring any number lower than 0 is going to bring it to 0, and any number greater than 0, it's going to print the output itself. Now we are compiling the model to summarize here. As you can see, we have the shape of our model, and as it's decreasing, as we have, this is the convolutional to the kernel model. Then we are using max polling 2, and then the dense layer. And then we have the custom callbacks class for login. Here we are creating just a custom callbacks class that is going to be called during the training. Then the training network, we are passing our data. We have 50 epochs. The validation data is the test images and test labels. And now let's take a look at these images, these results right here. Sorry. So we can see that the accuracy for our training data, it starts at 0.41, and for the validation data it's 0.505, and is possibly incrementing these values. As we can see right here, notice it's increasing the values. However, here we can notice that the validation values are decreasing, and we can assume that is because of the auto-fitting. So our model, instead of making prediction, the model learned and memorized the input data, and now it's printing all the values as are all the same. And we can see that in our image right here. As you can see, we have the training data, and this is the validation accuracy. When we get to the point, to the epoch number 40, we can see that it's changing the values right here. For here was learning right here, we can see that it's increasing a little bit. Then here reach, I would say, the top, and this starts decreasing since the model already memorized the input data, and we are going to have a constant decreasing value if we add more epochs in this model. So now, as I mentioned before, if we take a look at epoch number 40, we can see it reaches the top or the maximum for the analysis, and after that it starts memorizing the data and creating overfitting. Now the layers of this model, as I mentioned before, here we have the convolutional layer 2 here, right here, as in this example. Here we have the data, we have the nodes, the convolutional layer. So our convolutional layer is going to be here 32. Here we're going to have 32 of this size, and we're also going to have a 3 times 3 rows, 3 columns matrix, which is the values right here that are going to be randomly assigned. Let me show you how it works in the process of the operational convolutional operation. Right here, when the model passed as the input of the next model of the next layer, sorry. And I'm going to show you here. I'm using the fashion mix data set. This is the model that we have. So let's see. And here we have images of clothes. This is the matrix or the filter 3 times 3 rows and 3 columns, as we have the same in this in our model right here. And then we are going to pass the data, and the process is going to be it's going to be filtering the data and in a small matrices all the time, and the values is being computed since it's called the dot product or the of the operational convolutional, because these numbers right here, it's going to be multiplying the filter. So this number is going to go with this one, this number with this one, this value right here with the other one, and so on. So let me run the full process. In this exercise, I am using, as you can see here, the top edge filter. So I just looking for the top edge of these images. It's similar to what we did right here. Let me show you in the 2D kernel images right here. As you can see here, we said, hey, I just want to find the horizontal, I want to add the 45-degree lines, I want to find the 135. Here I want to find the edges. It's exactly the same we are doing here in this model. I'm just saying top edge filters, and the filter is right here. As you can see, we use -1 for black, 1 for white, and yellow for gray. So since we're analyzing the top edge filter, you can see here that the numbers are more numbers in red, which is a strong red, of the numbers of this model detected the lines, and it highlight these numbers right here. These neurons are more active, and these neurons right here are these are not the active neurons, these are negative neurons. Sorry, no, these are not as much active as the neurons right here. What I mean by negative neurons are these ones in blue, because it means this do the opposite of what we printed right now. So the line right here in blue might represent the top bottom edge filter, which is just the opposite, the bottom, sorry, not the top bottom, just the bottom. It's the opposite of these lines right here, and it's the same for all these analysis. That's how we are using this model. It's how these neuron words, the convolutional layer words, do this convolutional operation. It goes as fast as input of the next layer, and then we are going to have our output channel based on these random numbers assigned to our filters, that the filters are right here. So let's continue with our exercise. So as I mentioned here, we can see that at epoch 40 it started decreasing overfitting our model. We have the combination TD layers, then we have this max point TD. That what this layer do, it just calculates the largest or maximum value in every patch and the future map. Here we have our dense layer. This time we have 128. The activation its function it's really, and here we have this output layer or the output channel. We are want to have just 10 as output, 10 values, different values as output, and the activation on is softmax since we are looking for the probability. So now let me talk a little bit about each layer. So as I mentioned before, the convolutional layer, so right here, receives an input, then transforms this input right here, that it's called the convolutional operation. This is what the convolutional layer doing this part, then pass the output as the input of the next layer. Then we have the max point that selects the brighter pixels from the images. As you remember here in this example, here just picks the brightest point in our image right here. And the lens layer is the layer that connects each input to each output. Now in this part, I'm adding one more convolutional layer right here. As you can see here, this is our original one, and here I have added another one. I wanted to keep the same number of nodes for this layer. However, I changed the size of the matrix or our filter. So now instead of having 3 times 3, we are going to have 4 columns and 4 rows in this right here. The padding is going to be the same, which as I mentioned before, this is going to add just numbers right here. It's going to add padding actually to the model. Sorry, just one second. No, okay, never mind, but you already know what I mean. So we have our model, we have the epochs, the optimizer atom, we are using categorical cross entropy, and we are measuring the accuracy as a metric. So now let's take a look and let's see the differences. As you can see, the first difference is that in the epoch number 15 we already have a high value in our train data, and the same for our validation data. And this can be understood since in our model in this new model we are adding 32 more conventional layers, and right here instead of passing only one, we are having now 32 here and plus 32, and the difference is that here we're adding a small matrix of 3 rows and 3 columns, but now on the next layer it's going to be a matrix of 4 columns and 4 rows. So our model had more data to learn from, and we can also see that our model starts overfitting after epoch number 30. Then we start seeing that the accuracy validation it's decreasing, the same for the train data. At some point the model, it's for the train data it's almost 100%, which means that the model simply just memorize all the data, it's not making any kind of predictions. And here for the accuracy of the validation we can see it's also decreasing. And let's take a look at the plot, and as you can see here it's almost a constant linear line here, since the model already learned the data. And for the next inputs and outputs is going to be exactly the same. And as you can see, this is just summarizing all of what I mentioned before. After this epoch right here, we need epoch number 15, and the model starts looking with a high value. And if we look at the previous one, which is right here, and the epoch number 20 just started increasing the values in our model. Here was the epoch number 20 and 15. That's the main difference we can notice. And also that the model in the second model, it's memorizing the model throughout the epoch number 25 through the end of the model. Now I've added in the dropout layer to the model, using the same as the previous one, but here to dropout layer I'm setting it to 0.5, or to drop out half of the data, and we can start seeing better results. As we can see now, we don't have these high values. Now we can see that the model is learning from less data. And let me see the model to explain it right here. It's going to be dropout network. Okay, so here is what we are doing in our model. Before, in the previous one, it was like this. We passed our convolutional layers, we set the filter, we set the input shape, and all the information was passed through our model. But now, instead of passing the whole information, we are dropping out half of the information, represented by 0.5 right here. We are removing these nodes, I will call them, and then we are using the remaining set of data for our model to train and learn from. Now we can see the difference right here, as I mentioned, and also if we take a look at our plot, we can see that the model has improved a lot compared to the two previous one. And well, while we are dropping out the layer, as just mentioned before, we are just dropping these nodes to reduce the overfitting. So we want to prevent all passing errors. This one here, the input, okay, this right here, the input and the hidden layers in our model from optimizing their words as synchronously. This information right here, and this detection performed in random groups prevent all nodes from converging on the same target, thereby they correlating the weights, thus creating a new network architecture from the main network. Nodes are dropped with a drop of probability of p, which is exactly what we did right here. We can see here that we drop, and this drop is the probability of p. Let me show you here more information. This is similar to the image we have right here. Instead of passing now the 32 nodes, sorry, now we are going to have the half of this model. Now I am making more changes. We had before 32 here. Now I have 44, which means here we're going to have 44 instead of 32. The filter or the metric is going to be the same. However, the padding this time is going to be valid. I don't know if you remember for this exercise what I said. The valid it's going to be only this section right here. We are not adding any padding, so the output it's going to be different from the input. Okay, so that's what we are doing right here by saying valid. The activation is going to be rarely, kernel constraint is going to be to max norm equal to 3. The input shade, here we have the same. We are going to drop out a layer, but this time instead of 0.5 or 50%, I'm saying just 20% of the data, or the node, sorry. Here we compile the model and train the neural network with the model, and now the values, as you can see, are better than before. Now we can see that our model is not overfitting at any time. We can see that it's learning throughout the process all the time in each epoch.